Hi everyone, welcome to the third Keynote talk. Today we have Anders Hejlsberg. Ooh. And yes, let's see. Anders is a Microsoft Technical Fellow and the lead architect of the TypeScript open source project. Anders has worked on programming languages and development tools for over 40 years and is the original designer of C#, Delphi, and Turbo Pascal. Anders studied engineering at the Technical University of Denmark, and today he's going to talk about TypeScript. Please give him big hands.
Thanks, everyone. It's lovely to be here in person. This is actually the first in-person talk I've given since COVID. I think it's really kind of crazy, but it's lovely. I love it. I'm here to talk about TypeScript and the journey of adding static types to JavaScript. And that journey began more than 10 years ago. And back then, the world was very different from what it is now. What was happening, we were going from a very homogeneous world of PCs to a more heterogeneous world of devices and so forth. And Google had done fantastic work with V8 to increase JavaScript performance, and HTML5 was happening. And finally, the web platform was actually becoming a place where you could write real large programs. It was possible, and it was also becoming necessary because of the device revolution. And we all know that JavaScript is a language that has issues. And writing really large applications in JavaScript is just very, very hard. And the world was discovering that at a rapid pace at that time. JavaScript doesn't have a static type system. At the time, it lacked essential features like modules and classes and so forth. And it was designed in a hurry, and a bunch of mistakes were made in the early design. And the tooling for JavaScript at the time kind of looked like this. I mean, there wasn't really any at all, right? So you would write your code, you would hope it'd run, and if not, then, good luck trying to figure out why. And people were doing crazy things to sort of get out from under that, like writing in CoffeeScript, which is just another compiled to JavaScript language without a type system. So really, it solved some problems like classes and so forth, but not really all of it. Or internally, we were seeing people do wild stuff like writing code in C# and cross-compiling it to JavaScript. And that was actually how I sort of first got into this problem. Some folks from Outlook.com came to us and said, could you please consider productizing this thing called Script Sharp? And I'm, well, what's Script Sharp? Well, it's this thing that compiles C# to JavaScript. But why are you doing that? Well, because that allows us to use grown-up tooling. We can do code navigation, we can have modules, we can have all these fantastic things that, and I'm like, really? Is it really that busted? And that was sort of what got us thinking about, wouldn't it be better if we, instead of targeting JavaScript from other languages, what about trying to fix JavaScript? What is it about it that's busted, and what could we do to make it better? And we sort of ended up on two major things that we wanted to do. One was build great tooling enabled by static types. We knew already at the time from experience that you can't build a great IDE experience for a language that has no types at all, because there are no indications in your program as to what the intent is. And so statement completion and code refactoring and all of code navigation, all of that stuff just isn't really possible without some hints put in the code. And the other thing was ECMAScript 6 was becoming a thing, and it defined a whole bunch of new features, but the browsers were lagging behind, and so there were a bunch of features that people wanted to use, but they couldn't use because they weren't in the browsers. Yet it's actually possible to compile them into idiomatic down-level JavaScript through transpilation. And so those were sort of the two things that we wanted to do with the TypeScript project. So TypeScript, basically, it starts with JavaScript, to which we then add a static type system, and that enables us to build great tooling. And I just out of curiosity, how many of you use VS Code here? Yeah, a lot of people. And VS Code is written in TypeScript, and they were one of the original users of ours, and so they're sort of our sister project, you know, and you see what great tooling becomes possible when you add a static type system. But then through transpilation, it all just compiles back to JavaScript again. That's sort of, in a nutshell, what TypeScript is. The project today, we sort of operate by these 6 principles here. We are both open source and open development. The project is hosted on GitHub. It's a very active site, a repository, and then you're all welcome to check it out, please. We closely track the ECMAScript standard. We do not see it as our job to make language features in the JavaScript core language. Where we innovate is in the type system that we add on top. So we work with TC39. We've championed many features through TC39, but then we see it as our job to sort of invent and build and innovate in the type system. And then, of course, we want to build best-of-breed tooling. So the way we've implemented our compiler is that it is written first and foremost as a compiler for tooling's sake. And it is a service that the IDE can use to do things like statement completion, refactoring, code navigation, et cetera, et cetera. It's not just, you know, your classic code in and binaries out kind of compiler. We work hard to continuously lower the barrier to entry to make it easy for anyone who writes in JavaScript to use TypeScript. And then we focus a lot on the community, and it's a big community out there. So we released the first version of TypeScript in October of 2012. So 11 years ago, just about. And it's sort of been a slow climb, and TypeScript today is probably, it's for sure in the top 5 programming languages in the world, depending on how you look. On GitHub, this is the latest Octoverse thing. We're now sitting at number 4. And of course, if you add JavaScript and TypeScript together, it is by far the world's most used programming language. At this point, pretty much all major JavaScript frameworks are either written in TypeScript or for sure have support for TypeScript. And we try to work a lot with the community on making the experience better. We worked a lot with the Vue guys. We worked with the React. We've originally worked with the Angular folks, and that was sort of part of what got us launched years ago. And in addition to that, there's this wonderful community effort called Definitely Typed, which is all about collecting types for all of the world's JavaScript and putting it in a central repository. This is one of the most active sites on GitHub. Today, the activity is actually slowly trending down because more and more NPM packages now include their types, and so you don't need to get the types separately. They just come along when you NPM install something. But even so, this has been a large part of our success. Now, for the rest of this talk, I'm going to talk about the type system because that's probably what you're most interested in, and there is actually also where most of the innovation in the languages. And you know, when we set out to design this type system, our goal was to create a type system that models JavaScript's behavior. Or allows you to model JavaScript's behavior. And in a sense, that already sets it apart from how most type systems are designed, because most type systems starts with, you know, you design the type system and then that dictates what behavior is possible in your language, right? But here, we were coming in, there's a language that already has all sorts of behaviors, and it's now our job to design a type system to model that. And that takes you down a very different path, as you'll see. And you end up with a whole bunch of constructs that I haven't seen, type constructors that I haven't seen in other programming languages, and some unconventional choices also. So these are some of the attributes that I would use to describe our type system. First of all, it's erasable, meaning that this type system does not in any way affect execution of your programs, right? Because your programs run just as JavaScript. And when you write code in TypeScript, here's, for example, a little program that declares a person type and a greeting, and you see we declare a type person and we use it in a couple of places as a type annotation, but when this is transpiled or compiled, all of the types are erased, and what runs is this, just JavaScript. So the types in no way affect execution. And in a sense, what we're designing here is a type system purely for tooling's sake, which contrasts with most type systems out there that exist because you want to have certain runtime guarantees, or you want the type system to assist the code generator in creating the right types of instructions and so forth. None of that holds here. But on the other hand, the type system has to be completely interactive. The implementation of the type system has to be completely interactive because its main purpose is to power tooling. Now, we actually over time have accumulated multiple ways of specifying the types. Some people don't like to transpile their code. They like to just be able to save and run right away. And for that, a lot of people use what's called JSDoc type annotations. And we can slurp those up as well. We don't really care whether you use manifest type syntax or whether you put your types in comments. And indeed, when you're writing JavaScript in VS Code, you're actually using TypeScript. You may not know it, but the language service that runs underneath is the TypeScript compiler, because to TypeScript, JavaScript is just TypeScript with no type annotations in it, but we still can infer a lot of the types. Another aspect of our type system is that it's gradual. Of course, it has to be when you're in a sense modeling a dynamic programming language. In TypeScript, we have this funny type called any. This is sort of like a community meme there. Just slap an any on it, and then you don't have to worry about the types. And the any type is this oddball that is both a top type and a bottom type. So anything is assignable to any or compatible with any, but any is also assignable to anything else. And of course, that means you have massive holes. I mean, clearly this type system is not sound, and it was never designed to be sound, and gradual type systems aren't. At least not, they may be sound in islands, but they're not overall sound, right? And so here's an example of some code that you can write in TypeScript. If you wanted to, first create a number, then assign that to an any, and then assign that any to a function, and then try to call the function, and of course, boom, that's not going to work. But the thing that's interesting here is that we already have a runtime underneath where all behaviors are well-defined. So even this program has a well-defined behavior. The well-defined behavior is it raises an exception, which of course might not be desired. But there are no undefined behaviors here. And often one of the key things that people use TypeScript soundness in type systems for is to root out undefined behavior, because undefined behavior is what enables all sorts of security attacks and so forth. But in JavaScript, it's all well defined. It's just that a lot of the behaviors are undesired. And it's, in a sense, our job to tease out all the undesired behaviors. But that's a much, much lower bar. In a sense, we're coming at it from nothing is checked, and then anything we do makes the, makes the world better. Where most type systems come at it from a standpoint of, if you can't achieve perfection, then don't even try to go there. And that means you cut out a whole bunch of possible things that you could do that you might not be able to prove soundness for. But we don't have that restriction, and that actually makes our work very interesting, because we can go in places where people typically don't go. So I sort of describe our type system sometimes as a Swiss cheese type system. You know, it's full of holes, and in the most liberal settings of our checker, the holes are everywhere, right? But we actually enable and we recommend that you run the checker in strict mode, and in strict mode we can root out almost all of the things that you would worry about. There are no implicit any's ever inferred in that mode. There are only the ones that you explicitly ask for. Nulls are strictly checked, etc., etc. But again, we've in a sense turned the type system from a switch into a dial, right? And you can dial up how much checking you want. Now, our type system is structural, and as you all know, like JavaScript is duck typed, right? I mean, if you you write, if you know, if it walks like a duck, it looks like a duck, it's a duck. It's good enough, right? I mean, here's for example some code where we have a greet function that takes something that has a name property. And you'll see that we can either have a person class with a name property, or we can just pass an object literal. It doesn't matter. Anything that has a name property is compatible here. This is distinct and different from nominal type systems where, you know, you have to agree upon a name for every contract, and then you have to explicitly state that you implement this contract. And if you don't state it, then you don't implement it. And that actually creates a lot more friction in the system, right? Because unless two library writers agree on a protocol, well, they can't talk to each other without first writing adapters and Where in TypeScript, there is no friction, and also this enables us to actually add types after the fact. Which is really, in a sense, what powered the early success of TypeScript. At the time we came out, there was a gazillion frameworks and types for none of them, right? And so we had to provide a way of writing the types out of band in declaration files that are sort of like .h files in C, right? And being structural in the type system makes that an awful lot easier. The type system is also generic. I would posit that it is impossible today to create a language of any relevance that doesn't support generics. Go tried, but then eventually added generics as well. But when you combine structural typing and generics, you set yourself up for a world of pain, which we have spent the last decade exploring. Here's an example, say, of a generic type node, which is, you know, some node in a tree that has strongly typed child pointers. So the children, so parent is P, and then the children have node of P's as their type. Now, let's say I define another type that looks just like it in structure, but has different names and whatever. Well, in a nominal type system, these two would not be compatible. But in a structural type system, they have to be compatible. So let's say I have two instantiations of node, of null, the top root pointer of my tree, and now I want to determine whether these two are compatible. Well, structural means I have to go examine the properties of each of them, and yes, they both have a data, yes, they both have a parent of type null, and then they have children of type node of null and item of null, and now we go explore those, and then of course that leads us to, and that leads us to, and and it's turtles all the way down, right? And so you end up exploring these recursive abysses at all times, and you have to find provisions in the type system to cut off the madness. And so we have what we sort of call affectionately the turtle limiter. Did it show up there? Yeah. That we use various techniques to cut off the recursion after 3 to 5 levels, and then kind of go, well, let's assume that's true, and then let's check everything else. And if that also checks out, then we're going to say it's true. Now, we can get away with this because everything in JavaScript has a runtime type check built in anyway. So we don't actually have to prove beyond a shadow of doubt that this is true. We just have to prove it to a high enough degree of certainty, right? The type system also relies heavily on inference, which of course you want to do because you're starting with something that has no type annotations in it. And so to the extent that we can infer stuff, it's good. Here's an example of a program where everything is typed by a single type annotation on get lengths. And because strings is of type string array, then we know that there's a map function, and we know that map function takes a function, and we can type the s accordingly to be a string, and that means in turn that we can figure out that s.length is a number, and that means that we know the map returns a number array, and that means we know getLength returns a number array, and that means we can infer that length is of type number array. So the types can flow throughout. Now you might ask, why do you even need that type annotation? Couldn't you have inferred that from the call to getLength? We could have, but we don't. And so unlike other type systems, like say Milner type systems, for example, that do unification and a whole program analysis to deduce the types, we only do inference from context moving inwards. We do not have spooky action at a distance, if you will, which often plagues some functional programming languages where you have a call in a remote place that all of a sudden changes the types over here. And of course, full program analysis doesn't really work very well in module systems, right? Because so that means that the module barriers are going to have type annotations anyway. So we stipulate that functions must be annotated. The only time we infer for functions is when there's context, like for example, you're passing a lambda here. At that point, we can contextually type from the outer context. But getLength, a top-level function, we do not infer anything. The type system is also very expressive, and this is what I'll try to cover then in the remainder of my talk here, all of these various type constructors that we have, and that we have accrued over time. Of course, we support like object types, you saw some examples of that. We also support union and intersection types that basically union or intersect the domains of possible values of the types. We support the KIA for index types, which obtains the set of possible property names for a type. And then lookup types that takes, given a type T and a key of type K, what is the type of properties in that type? And then map types, which are comprehensions over object types that allow you to do mappings. And all of these exist, conditional types. And now we're getting sort of into dependent typing and whatever, and I'll show you some examples of that. But know that all of these exist because they are necessary to model JavaScript's behavior. It's not something that we did just because we thought it was fun. It's actually something that is needed in order to properly type JavaScript. And that's what I'm going to try to look at now. Let me go here, and I'm going to start showing you some code here. First, I'll talk a little bit about union types and how they, oops, is this not showing my screen? I guess it's showing my, that's interesting. What do I do to get PowerPoint to show me my screen? Well, maybe I'll just shut down PowerPoint. That'll probably take care of it. Here. Let's see. Yowza. How's that? There we go. Can you all see this? Okay. This is a very typical piece of JavaScript and a very typical pattern in JavaScript where you have, JavaScript doesn't have overloading, but it's dynamically typed. So you can write a function that does something when you give it a string and something else when you give it a number. And this is very common in JavaScript. Maybe not strings and numbers, but it's very common to either take a string or an object with a property bag or whatever. And then you want to tease out inside the function what was given to you, and you do that by guarding code with type checks, and then off you go. Now, originally, TypeScript did not have union types. We were basically a singly rooted type system, and that made it pretty hard to type constructs like this. We did originally introduce overloading, but that only works at the top level, not when types are buried as the types of properties and so forth. And so here, there was really no type that I could give here. I mean, I could give it type string, but now it errors on one of the things that I want to permit, or I could give it type number. and then it errors on the other one, or I could give it type any, but then it doesn't error at all. That's not what I wanted either. So with union types, I can say this is a string or a number, and now I get the desired behavior. And so union types allow me to basically combine the domains of arbitrary types into one type. And probably this is the most profound thing that we introduced into the language. It has since colored everything that happens in the language, and every operation does not operate on a single type. It always operates on a set of types represented as a union, and the singleton case is just sort of like the oddball. With union types, it also makes it possible for us to meaningfully increase the precision of the type system. So shortly after union type, we introduced literal types, which are types they're basically unit types. They have a single possible value, which is the literal. So here, I am making a new type called direction that has 4 possible values, up, down, left, and right, represented by their literal types. And that gives me much, much higher precision than what I could have otherwise had, but is really not meaningful in a singly rooted type system. I mean, you know, what's the point of something whose type is always the same, right? I mean, that's a constant. But once you have union types, you can combine them. And of course, this occurs. I mean, just if we look in the type declarations for the DOM, this occurs all over the place. Super, super common to have properties that have these like 10 possible values and whatever, and this allows us to model it and type check it properly. And of course, it also makes the code authoring experience better. When I'm sitting here and I'm about to type in what can go here, well, statement completion can help me fill in the right types here and show me and so forth. Now, this stuff also helps with solving the billion-dollar problem, or the of null pointers, or the $2 billion problem, if you will, in JavaScript, because JavaScript is endowed not just with null but also with undefined, you know, and they're but really we can use the same techniques to chase these issues down. And you'll see here I have a function that takes an optional message, and if I attempt to say message.length, here you'll see we give statement completion, but if you choose length, let me just say let len equals, you'll see that we use the question dot operator because we know in statement completion, because we know the value could possibly be undefined, and that means we propagate the undefined, and so len is actually number or undefined here. And if I were to get rid of the question mark, you'll see that it's an error because we know from control flow analysis that it could possibly be undefined. But if you're in a guarded block, then indeed now you can choose these or pick these methods. And so this is enabled by control flow analysis, and that's sort of another part of, once we had union types and literal types, we added control flow analysis and type refinement based on proof in the code of, for example, here, this constitutes a proof that message couldn't be undefined, and since message is a union type that includes undefined, we can remove undefined from that union type in the code that's guarded by the check. And the check isn't just a syntactic check that you're enclosed in a block. It could also, if I said here, if let's say if message equals undefined, throw new error, for example, you'll see here that message now has undefined removed from its type, because we know from control flow analysis that code dies and never reaches this point here. Indeed, maybe I'll skip over this one here because it takes a little while to work through, but here you see, again, examples of where control flow analysis, you know, detects uninitialized variables, detects type mismatches, and so forth, and chasing them down is interesting. In fact, it's funny to look at part of the issues that JavaScript has is the semantics of the operators. Let's say I have a function here that takes strings or string arrays or nulls or undefined, and I do a truthy check of S. Well, in here, not surprisingly, you get string or string array. But down here, you get null or undefined or string, because the empty string is falsy. And so you could still have a string here. Now, a lot of people forget these things in their code, and they end up thinking that they have guarded against a certain type occurring, but they haven't. Here's another classic. If type of S is object, you would think, well, I probably only get the string array then, right? Well, no, you also get null. Because null, the type of null, is object in JavaScript. No. Don't ask me why, but it is. And so down here, you get string or undefined. Or if you use, if you use the double equals to check for undefined, well, then you actually also check for null, because it coerces the values. But if you use triple equals, then you'll see you only get undefined, and null now occurs down here. And so knowing this, I mean, we on a daily basis, we get bug reports where people go, I wrote this code and whatever. No, actually, it's because you did this and this and this and not that. And so, you know, so this is something that people always struggle with. Now, one of the really, really interesting things about union types also is that they enable a pattern that we call discriminated union types, which this is a very, very common pattern in JavaScript, where you have objects that have a discriminant property that says what kind they are, and then the remaining shape of the object depends on the kind. Here's like drawing shapes or whatever, but this could be a message processing system that receives JSON over the wire and then, you know, branches out based on it. It occurs everywhere in JavaScript, this pattern. And we actually understand this pattern. So here you see a function that computes the area. And all I have is a single type annotation that says S is a shape. And that means we know that S.kind could be square, rectangle, or circle. But then if you branch on that, then we also know in here that S now has been refined to just be the square variant. And that means that in turn we can give you statement completion. So when you say S dot, we know that size is one of the properties you can pick out here. And similarly for rectangle and circle and so forth. But even better, if I try to put code here, we actually know that this code is unreachable because you have handled all of the cases that could possibly occur. And so through control flow analysis, we know this doesn't happen. And so exhaustiveness checking is, in a sense, falls out from this work. And now you can sort of see it's kind of like ADTs in a functional programming language, right? There are certain patterns that you could do here that I mean, yes, no, there's not pattern matching with the same level of richness necessarily, but even that can be worked around. It's also interesting to note that the type of S here gets refined down to never, which is the empty union type. We used the name never because it originated originally in functions that we know through control flow analysis never return. So if a function throws always, its return type is never, meaning that you can assign its result to anything because it'll never happen. And so never is this bottom type that is assignable to everything and is the opposite, if you will, of unknown, the top type that isn't assignable to anything, but everything is assignable to it. Now, interestingly also, you'll see that because we know that the function the endpoint of the function is never reachable, we can infer that this function returns number because we know that all of the return paths produce a number and there's no fallout at the bottom that could possibly return an undefined. But if I comment out one of the cases, you'll see now that we know that S here could possibly be the rectangle, and this is no longer unreachable, and the function now returns number or undefined because you could fall out the bottom. So there's a bunch of stuff here that combines to really find a lot of bugs in people's code that they didn't realize they have. Now, the complement of union types is intersection types. They are less often used, but you very quickly discover that if you have unions, you also need intersections. Here's an example of where they are relevant. Let's say I have a function that takes string and returns string, and a function that takes direction, that was that up, down, left, right that you saw earlier. And let's say I make a union of those two, and now I want to call this function. Well, intuitively, you sort of know that, well, I'm typing two input positions here, one that requires strings and one that requires just the 4 possible string literals in direction. So the only thing that's safe to pass in is one of those 4 values, right? But on the return, I don't know which one I have, so it actually returns a union of the two, which is just string, right? And so effectively, you end up with intersections in contravariant positions and unions in covariant positions, and the type checker knows that, and that's one example of where intersections are a must once you add unions to your language. And indeed, you can see here, if I intersect string and direction, I get string, but if I union string or direction, I get string, but if I intersect them, I get up, down, left, right, or direction. And interestingly, if I have a string or a number and I intersect them or union them, then I get string or number. But if I intersect them, I get never, because they share nothing. And so if I were to change this to string function to numfunc, you'll see that I end up with a function to which I can never pass a value. But if so I can never call it, but if I could, it would return a string or a number. Other examples, I'm going to skip over this in the interest of time here, but indexing with union types, the same thing happens. If you do spreading, we approximate the behavior of spreads using intersection types, which isn't exactly correct for JavaScript, but it's correct enough for our purposes. Let me try and look at some of the other stuff that we do. Here is a very typical pattern in JavaScript, and now we're starting to look at some of the things that you can't really do in other programming languages, but are typical in JavaScript. Let's say I have an item record here, and then I write a function that takes an object and a property name and returns that property of that object. Now, this is a capability in JavaScript that strongly typed languages typically don't have. Every object in JavaScript, in a sense, is a dictionary, and you can treat the property values just as keys in that dictionary. But so, how would I type that? How would I make this piece of code down here actually give me, for name, something of type string, and for price, something of type number? Currently, it just gives me any, as you can see, because I don't have any types. And so I'm gonna type out what it actually looks like to and here you'll see two of the type constructors that I mentioned earlier in use. So what I'm saying here is now getProp is generic on T, which is the type of my object, and K, which is something that extends the possible property names of T. And then we infer that the function returns a T sub K. And now you'll see down here that we infer, oh, you passed me item and name, and that gives me back a string, or you passed me item and price, and that gives me back a number. If I, for example, said greater than equal, it doesn't matter, then pass price, else pass name, well, you'll see that we now infer, well, you're passing me either a name or a price, and therefore you either get back a string or a number. And so unions distribute over this type constructor, the T sub k type constructor. And there's a whole bunch of semantics that you know, over time we've sort of learned about these type constructors and how to check them and what are their constraints and so forth. And a lot of the reasoning in the checker, you know, revolves around that. Here's another real-world example that maybe I won't spend too much time on, but this is something that exists in the real world in a Lodash library, a pluck helper method that picks out, given an array of T's and a key name, pluck me out all of the properties from those objects with that property name. And that, in turn, is an array.map where X is typed as T, and it returns a T sub K, and therefore the result here is a T sub K array, and therefore down here I get a string array when I pass it, et cetera, right? Map types are, in a sense, the ability to apply comprehensions to types. So it's like sort of like a for comprehension that computes the properties and their types inside an object type constructor. Here, for example, you see I say for P in foo, bar, and bass, give me a property of type string, and what I end up with is this type, right? Now we have a bunch of built-ins. For example, there's a, gosh, I keep doing that. There's a built-in partial type constructor. If we look at its declaration, it says, given a T, iterate over all the keys of T and make them optional and give them the type that they already have. And so this takes an object type and makes it into an optional type of the same shape. And there's pick that says, give me an object type and a set of property names for that object type and pick out those properties only and give me a type for that. And here you see examples of use of that, like an assign function that, for example, takes a partial set of properties and modifies them, or a pick that picks out, you know, two properties from item, which in turn ends up giving me back a well, if you look at what we get when we say statement completion on X, you'll see that we picked out just those two properties. So there's a whole bunch of pattern, and the reason we have those is that this is what a lot of JavaScript libraries do. They do sort of object munging and turning objects into other objects and turning their properties into different properties and so forth. And so we're sort of guided by what people do in what we go implement in the type system. Now, one particular example there that starts to get really interesting, and now we're starting to get into dependent typing, is conditional types. So here's another JavaScript pattern that we see a lot, where depending on the input to a function, you get different outputs from that function. Here, for example, if I give you a string, I want to get back a name label, but if I give you a number, I want to get back an ID label. And ideally, we would want down here, you know, we would want typing that gives me the right type when I give you something that we statically know is one or the other. And that becomes possible with conditional types. So here instead, we've said a label of T, where T could be a string or a number, is if T extends string, then a name label, otherwise an ID label. And then we use that as the return type. We may create label generic, and we use that as the return type. And now when I pass in Elmore, I get a name label, but here I get an ID label. Or if I pass in one or the other, I get one or the other. So in a sense, you can think of conditional types as smart union types that collapse upon instantiation to one of their possible choices. Now, this then combines with inference as well. And this is where it starts to get interesting, because now you can write logic. So here we have a result of T that says, if T extends promise of mumble, then return the mumble, otherwise return T. And now if I say, what is a resolved of string? Well, that's string. And a resolve of promise of string, well, that's also string, but a resolved of promise of string, well, it only unwraps one level. So it's not quite doing what I want it to do. But we actually allow, we actually allow recursive types combined with conditional types. And now it's starting to smell like Turing completeness because now types can compute and iterate. And here you see that now we will unwrap as much as we need to. So even here we get string, and here we get all of the bottom types unwrapped out of their promises. This turns out to be very common in JavaScript too. There are lots of places where we need stuff like this. For example, there's an array, a method on array now that got introduced recently called flat. That flattens an array. So if you put arrays inside of arrays inside of arrays, then there's a method that flattens them all into one array. And typing that looks something like this, where no matter how many levels of typing I give it, it flattens it down to one level. And of course, if I try to trick it and construct an array that every time I index it, I get another array, and it just goes on ad infinitum, then you'll see again here we have one of these turtle limiters that we have built into the type system, where after 100 iterations or whatever we go, this isn't going well, we're going to stop here and give you an error. Now, chasing down all of that is actually what has been the really hard part of and something that we continue to struggle with, because effectively our type system is Turing complete. And someone even put up an issue that proved the Turing completeness, and people are doing the most absurd things. I've seen people write chess games in our type system, SQL parsers, you name it. But lots of stuff is possible. Here's an example of how to reverse a tuple, and you see that this really is a nice little pure functional programming language in the type system, where you have iteration through recursion, and you have choice through conditional types. All of the values you operate on are types. So you're operating on sets of values, but of course they could be singletons, and now you're just operating on simple values. And your functions are your generic types, because they take other types as parameters, and you can invoke them again, and so forth. And so here you see that, yes, you can write something that reverses a tuple, for example, in our type system. How are we doing on time? Sort of okay. Let's see. Where would we go next? Let's look a little bit at tuple types, which is interesting too. And then I think I'll stop after that. So we support arrays and tuple types, and we even allow tuple types to have holes in them. So you can say, well, the number array, here's a thing that, so first of all, in JavaScript, tuples are just arrays with a given fixed layout, right? And so a two tuple here of number comma string is when you run the program, it's just an array with two elements, but we can strongly check this. And we can even have holes in the middle of arrays of a certain type, and then check the front and the back. Where this gets interesting is JavaScript has all of these abilities to manipulate argument lists of functions. And for example, here's a function that takes a number and a string, and I can pass to it 1, ABC, but I can also spread in a tuple, provided that tuple has the right shape. And indeed here, if I were to try to pass in A3, you'll see our checker says, no, you can't do that, but you can pass in the A2 tuple. And functions also support REST arguments, where you can spread in arrays. And indeed, if you type a REST argument as a tuple, you see that everything actually unifies. This simply becomes a function that takes 2 arguments, right? So there's really no difference between parameter lists and tuples. And that in turn means that we can type parameter lists as arrays or tuples and then capture them. So here, for example, we're capturing the tuple that comes out of calling this function. And that is, in fact, precisely what all the function does is this. And we can give accurate type to that. And when you spread in an array, of course, we give you a number array. And we can even, in later versions of the language, allow you to control whether you want us to infer mutable types or immutable types. Here we infer an immutable type because both have good uses in the language. This is another part of inference that differs from functional programming languages. Often, like in a functional programming language, you're free to just infer the most precise type ever, every time, right? But you don't really know in a language. When you said 1 as the element of this tuple, did you mean you want a tuple back that has numbers in that position and then you might put other numbers in there? Or did you mean something that you're never going to mutate, in which case we want to type it as the literal 1, right? Because that's the most precise type you can get. And so it's not always decidable, and so we allow you to put in hints like that. Now, where it starts to become interesting then is you can model higher order functions as well. Here you see an invoker that calls a given function with a given argument list, and we can give accurate types to that. So when I say invoke of F1, you'll see that not only do we know what its type is, but we know that you are now supposed to give me an argument, a number and a string, and we can even pick up the parameter names from the function you passed in. And so again, these are very common things that happen in JavaScript, and so over time we've enabled you to model that. The last crazy one here is inferring to composite tuples. This is starting to look a little bit like currying, but it's really just binding arguments to functions and understanding how to split the argument list of the function into 2 tuple types where 1 is specified, and so now you sort of get partial application in all of these with the correct types. I'm going to cut it off here and maybe just do my summary slide, but hopefully this gives you sort of a taste of what's possible in this type system. I wanted to just sort of end on a slide that talks a little bit about why I think TypeScript succeeded. One of the key decisions we made early on was to not try to create a language that replaces JavaScript, even though the world was crazy with languages that were supposed to replace JavaScript, but rather we went for the other route of trying to improve the existing ecosystem. And I think what we also got right from the beginning was that we were designing a TypeScript system for tooling's sake here, and this was all in the name of providing and creating excellent tooling. And that means that you engineer your compiler very differently. You engineer it as a compiler that really works as a service that powers your language service underneath the editor, right? And that is, in a sense, its core purpose. And that means that everything has to be deferred and incredibly responsive. I mean, we know from user studies that users get irritated if it takes more than 250 milliseconds for the drop-down to show up. But if you're sitting in a 100,000 line program and you press dot somewhere arbitrarily in the middle of this program, you obviously can't check all 100,000 lines to deliver a result. So you have to be incredibly incremental, yet the minute the user then completes that dot, then the program has changed, and it could mean something completely different. So you also have to account for that, and and that is not simple. And the TypeScript compiler is, in a sense, a gigantic exercise in applied functional programming. If you look at it, where we construct ASTs for all of the source files, and then we never mutate those. And every time you type a character, we throw away the entire program, and then reconstruct it from pieces of the old program that we can convince ourselves are reusable. And that's how we get our performance. And of course, I should say, TypeScript is written in itself, and writing a compiler in JavaScript is not the first thing that I thought I was going to be doing for a decade of my life, but it's amazing what's possible. Yeah, I'll leave the rest up there maybe, and then I'll just let you read it, and then we'll stop here, and then I think there's time for a few questions if people have some. So thanks. Yeah.
Thanks a lot for the
you're welcome.
yeah,
Yeah,
inspiring talk, and we have so many questions. Let's start with Ron, when the mic is ready.
Hi, thanks very much for such an interesting talk.
Thanks.
I was wondering, when you're retrofitting a type system on a language, you're trying to avoid undesirable behavior, but along the way, at some points, you throw out programs that would have desirable behavior.
Correct.
So I was wondering how, as a group, do you decide which programs you want to save, and how do you decide when to add switches to turn the dial? What kind of thought process goes into that?
It's a damn good question, and it's not one that has a short answer. But I think a lot of it is based on our own experience using the language first. We dog food every day, and so we know what the patterns are, and we know that when it's irritating that we can't get them right. We also judiciously monitor the issue tracker on GitHub, and so the community is very good at making us aware of issues and providing programs that reproduce the problems, and then we try to jump on that and make it better. But it's an iterative process all the time, and it's this tension between completeness and soundness. You know, the answer is never at the extreme. It is in this nebulous gray middle, right, where that we try to chase down in our day-to-day lives. Yeah.
Thank you.
You're welcome.
Thanks, Adam.
Hello, I'm Adam Chapala from MIT, and I'm wondering about the principle you shared where you can kind of make a best effort when it comes to the soundness of different typing constructs, because there is dynamic checking that was always there underneath in JavaScript. What about important properties that have not been dynamically checked, like around encapsulation and data abstraction, where you could really foil some effort to maintain an invariant if there was some corner case of the type system?
Well, this is why we have these varying, I mean, first of all, that's why we have strict mode, and we recommend that people use strict mode. And in strict mode, it is a lot harder to violate soundness, but it's always possible, because, I mean, we do have like assertions where you can just willy-nilly assert that this now has type that, but we endeavor to make all of that explicit. So it only happens if you say so. And if you say so, fine. Then you get to say so. Indeed, we have this thing called user-defined type predicates, which are functions that you can pass an argument, and then you can assert in the return type that X is of type blah. And then you write the function that proves it. Because there is no definite proof in JavaScript that you implement this particular protocol, and most of the time it's based on this good enough. Okay, if you have that property and that property, fine, we're going to say you're that. We're not going to check all of the 50 possible properties, because that would be too costly at runtime, right? So it's always this balance, of safe enough, right? And we sort of have to embrace that in the design of the type system. We can't fight it, because then our tool is of no interest to the community, right? So again, it's tricky.
Thanks.
Yeah.
Hello, I'm Simon Peyton-Jones.
Simon, how are you?
Anders, it's good to see you. Although I used to work for Microsoft,
I know.
I have learned more about TypeScript in the last hour than I have in the previous 10 years. So thank you for that. So my question is this. You described a bit of a Wild West situation in which the bar is very low. You can't not improve the situation, so that's great. And yet, I'm sure there is some correctness criteria that's in your head. Like, you don't want to report an error when there really isn't one. And you describe quite a complicated system. So I bet that somewhere in your head or on paper, there's some formalization of stuff that says, well, here is a criterion that says this heap of code that is the compiler is doing the right thing. Do you have such a thing? Or even sort of sketches of
I
such
do,
a thing?
but
Something
in
that means
that,
it's more than just defined by the implementation.
yes, but in that heap of stuff, there are a bunch of unsolved problems that we don't know the answer to. For example, I mean, one of our most one of the issues that practically on a daily basis we refer users to is issue number 9998, which talks about limitations of control flow analysis. For example, it is possible in JavaScript, which is one of the things they got right, to close over outer state, right? So nested functions can access the outer locals of outer functions. Now, what if you write, let's say you have an outer local, and you say if that outer local not equal to undefined, and then you have a block of code, and that block of code calls functions. Well, do these functions then, I mean, and it's like, how do you, now you could try to inline the world there and see and whatever, and it's just, there are certain things that you either, but you still have to say, does this check for undefined hold in the face of a call to a function following that function call? Yes or no? And you're damned if you do and you're damned if you don't, right? Because some people will go, yes, that should invalidate all of my assumptions because every call to a function in JavaScript is virtual and you have no idea where it's ultimately going to go. So it could have, but does it? And in reality, 98% of the time, it doesn't, you know, and it's inconvenient. And so there's that, right? There's just these things that we know we will never solve. And so it's just about like making the right choice, and then every time someone arrives and tells you this is wrong, we tell them yes, but the alternative is worse. So
you could. I was wondering whether you tried to distill some of those choices into some kind of formalism other than the code of the compiler itself.
We have not been particularly formal in our design. No, I was so. But hey, if you're interested, yeah, I'd love to. Exactly, and I would love to learn a lot about what other holes we have that I didn't even know about. So yeah.
Hi, Sam Tobin-Hochstadt, Indiana University. So thank you for the very nice talk. As someone working in gradual typing for a long time, it's been very gratifying to see the amazing product that you all have produced building on those ideas. And I guess my question is, what would be valuable for the academic community, say those of us who think about gradual typing in a research context, for you? What questions are the next ones that people should be thinking about for TypeScript in 5 years, or for the next gradually typed language that comes after TypeScript that we haven't solved those problems yet?
Well, I mean, for me, probably the thing that gives us the most headaches is because we're Turing complete, you can do infinite computation with our types, and how do you cut off the madness, and where do you cut off the madness? And does there exist proof that certain types terminate and others don't? We're not super good at like, I mean, we have some fairly crude limiters in place, you know, that will stop recursing, but at times they stop recursing too soon, and then all of a sudden, after 3 or 4 levels of nesting, things are not checked as much as you would like them to be. But conversely, there are examples of types that absolutely explode exponentially after 3 or 4 levels of nesting because of the generative nature, and it's very hard for us to tell the complexity of a type and how far to drill into it. Do you know what I mean? That is something that for a decade we've struggled with. And we still, I mean, just yesterday I was fixing a bug in this particular area, right? And again, it's just, so I would love more research in that area. That would be super, super interesting because we would put it to good use if we knew better answers than the answers we have now. I'll keep going as long as you want.
Yeah.
So yeah.
5 more minutes, 4 more minutes.
Yeah, go ahead.
Hi, I'm Neil Krishnaswamy from the University of Cambridge. So I wanted to ask a question about the intersection and union types in TypeScript. So, you know, this is one of these features where the natural complete strategy has exponential backtracking, but there aren't like, you know, clear heuristics like cutting off recursion depth at a certain level. So, but TypeScript is still quite responsive. So I was wondering, like, what kind of heuristics do you use that you do find work well?
Well, so union and intersection types are rarely an issue. There are certain constructs you can do where if you start intersecting large union types, then we do this thing we call normalization, where we bring them to sort of a first normal form, and that actually is quadratic in nature, and so types can get very large there, and we do not, as a rule, operate on denormalized types. We always normalize such that unions sit above intersections, sit above singleton types in the type representation, that's not without issues. And so we do have certain limiters in there that say this type is too complex to compute, and we're not going to try, because otherwise it's going to take all afternoon. But generally speaking, I think where we really run into sort of intractable trouble is because we allow recursion in the type system and computation through conditional types and recursive types, and those can run amok. And sometimes they run amok by creating millions of types, but they're still very shallow because they're very bushy and wide. Do you know what I mean? And it's hard for us to get those always. And so people in the community get very inventive when they type their libraries, and they're very proud of, oh my God, look what I accomplished here with this morass of types, right? But they explode in your face, and then of course all the users of that framework are now burdened with statement completion that gets incredibly slow, and so that's always tough. It's tough because it's tough for us to place blame because we don't know what's causing all this computation. Do you know what I mean? Or not easily, at least. So yeah, those are some of the things that we struggle with.
Okay, thanks.
Hi, Mike Sperber, Active Group. So at least with static type systems, as they evolve, sometimes you make changes that break a lot of users' code. Was that ever the case that you wanted to make an improvement to the type system, but then you discovered?
Oh, absolutely. And it's sort of the strange dilemma of a type checker's job, right? That as the type checker gets better, it produces more errors, and therefore it breaks people's code. Because, hey, this built before with the last version of the compiler, now it says there's an error here, but obviously the program is working. Well, there could possibly be a condition where your program errors, but it doesn't in real life. But do you know what I mean? And so it's that debate always. We tend to weigh changes on, is this something where our current behavior is just blatantly wrong? And yes, we can defend no matter who arrives, we can defend and go, but look here, I mean, clearly, this should not do what it's doing now, so therefore we're going to fix this, we're going to call it a bug. But then there are other situations where, yes, we now start checking more judiciously, and that is going to break some common patterns out there that, people obviously have worked around in their existing programs, and it's not actually causing them grief. At that point, we typically lump it under a new strict option, and then you could opt into it. And then we have this uber option called strict that always opts you into all of the new strict options. So if you're in that mode, then you just get the latest and greatest, and then you can opt yourself out of the latest checks if you don't want them. Or you could start at a baseline where you're not strict, and then you opt yourself in individually to every new feature that we add. But of course, as time marches on, we get more and more compiler options, and that in and of itself, and like testing all the combinatorics of that is horrendous, right? And so I don't know that there's a fantastic answer, but we try to cater to those sort of two standpoints, if you will.
So let's take the
last question. Yeah.
Yes.
I want to elaborate a point that you didn't mention, but if you're using TypeScript, you're also allowed to keep some files as JavaScript, which is super, super useful when you're trying to migrate something that is not really well typed. Just okay, this is going to be JavaScript, and I will slowly type them down. I've successfully migrated a bunch of code base this way, and it works really well in practice. But my question is a little bit off a tangent. Tooling and compiler as a surface model is a really important part of the TypeScript. It is also a really important part of another Microsoft project, the C# Roslyn compiler.
The which, sorry?
Sorry?
I didn't hear the last part. It's also an important part of
the C# Roslyn compiler.
Yes, yes.
Yeah. I guess I'm wondering which one came first, or like how much like intercultural crossbreeding between these two compilers are happening inside Microsoft.
There was actually a lot of crossbreeding in the beginning. Roslyn came first. And indeed, the first production compiler, the first compiler that we shipped or released for TypeScript was actually written by several of the people who had been on the Roslyn team. And that was actually also an interesting journey because they came over and then they proceeded to write a TypeScript compiler in C# style in JavaScript, right? Lots of classes and lots of auto-generated syntax trees, AST accessors and blah, blah, blah. And we had an awful lot of auto-generated code right off the bat. And that's actually not a good way to get performance in JavaScript. And then we got more interested in this more functional way of writing JavaScript, where you just write functions within functions, and that's how you get isolation of state and whatever, and that's also how you reduce polymorphism in your code, which is pretty bad. V8 handles polymorphism pretty badly, and it doesn't know how to inline when you make method calls because everything is virtual in a sense, right? But if you have functions within functions, then all of your calls are inlineable, and you get a whole different level of efficiency. And so currently, the TypeScript compiler is implemented pretty much, there are no classes at all. It's all functions. It's a large exercise in functional programming in JavaScript, if you will. So that was an interesting journey too, yeah. There you go, yeah.
Great, thank you. So let's
all right,
thank
well, thanks all.
Anders
Thanks
again.
everyone.